we are given three formulas, and we have to prove that the third formula as a conclusion is a logical consequence of the two other formulas as premises. And we have to use SLD resolution for that. Since we want to apply resolution, we definitely need to translate all our formulas into CNF, but first, of course, we need to formalize those statements. So this is what I'm going to do. And of course, since we are now in a predicate logic, we must introduce our predicates first. So what our predicate should be? Let's see. So if you look at the sentences, it's quite obvious that we need a predicate for getting a promotion. So let me introduce PRX for X as a person is promoted. Then what other predicate do we need? Well, we need another one for being the CEO's favorite employee. So let me introduce the predicate CF of X for denoting X is the CEO's favorite employee. And similarly, we need another predicate, let's say DF of X for being X, for X being is the director's favorite employee. Okay. And we don't need any other predicates, only those three. So let's formalize the first premise. Let me just denote it as P1. Some who got promotion are the CEO's or the director's favorite employees. Since the sentence starts with the word some, you can guess that this formula is going to be existentially quantified formula for all exist X, such that, well, X definitely got promoted. So PRX, and X who got promoted is the CEO's favorite employee or the director's favorite employee. So you have to continue with the disjunction CF of X or DF of X. Okay, let's continue with the second premise. Among the director's favorite employees, only those were promoted who are favorite employees of the CEO as well. Well, it's not that easy to decide if the next formula will be universally or existentially quantified one, but probably you can feel that this sentence is about all the possible employees. So it's a universally quantified statement. So let me use for all X, and then it's quite obvious that we only have to talk about the director's favorite employees. So we need to filter all the possible values for X to the director's favorite employees. So this is why I'm using DFX here. And how to continue? Only those were promoted who are favorite employees of the CEO. And PRX implies CFX. So basically, the formula is about checking for all X that if X is the director's favorite and he or she got promoted, then he or she must be the CEO's favorite employee as well. Okay, maybe it's not that easy to see why this is the correct implication, but actually it is, since what we want to conclude is the person X is the CEO's favorite employee, and there are two prerequisites for that. First of all, he or she must be the director's favorite and got promoted. Okay, let me formalize the last statement, the conclusion formula. There are a few favorite employees of the CEO who got promoted. Of course, this is going to be an existentially quantified formula. And so I'm using exist x, and x must be the favorite employee of the CEO and must be promoted as well. So let me translate the first formula into CNF. Since in CNF, no existential quantifiers are allowed, we must eliminate the existential quantifier. And on the other hand, we must substitute the bound variable with a new Skolem constant, such as C. So this is the process of Skolemization. And actually what we get is in CNF already. Actually, it consists of two clauses, PRC, and the other clause is CF of C or DF of C. Let's translate the second formula into CNF. First of all, we need to eliminate the implication, which means we have to negate the left-hand side, which means after applying the De Morgan laws, we must negate df of x, or the negation PR of x, or CF of x. So this is the clause, and of course, the universal quantifier must be used in this CNF. So this is a universally quantified clause here. Okay, last but not least, we have to do something with the conclusion formula, since we want to apply resolution and to prove a logical consequence. As you already know, we must negate the conclusion formula, which means that we must change the quantifier to the opposite. So the existential quantifier turns into an universal one, and also all the literals got negated, and the conjunction turns into a disjunction. And this is already a clause here. Okay, so let me just take all the clauses and put them in this list of clauses. PR of C is the first clause. The second clause is CF of C or DF of C. The third clause is for all x, not DF of x, or not PR of x, or not, or CF of x. And in order to make all the clauses as transparent as possible, I'm not going to display the quantifier. I already explained this before, since in CNF, in predicate logic, only universal quantifiers are allowed. We actually know that every variable in our formulas are universally quantified. This is why we don't need to display the quantifiers. And therefore, the fourth clause is not CF of x or not PR of x. So these are the so-called input clauses. This is the input clause set here. And I would like to highlight this because when applying SLD resolution, input clauses play a very important role. Okay, so let's try to construct an SLD resolution derivation from this input clause set. So how to do this? We have to pick two clauses at the beginning. Let's say I'm picking clause number 1 and clause number 4 and generate a resolvent. Of course, in this case, we must apply unification. We must substitute x with c. Otherwise, those two clauses would not be resolvable. And the resolvent now is CF of C. Okay, since SLD resolution is a specialized linear resolution, we must reuse the latest resolvent, clause number 5, and we must choose a psi clause for it, a CF of C. So what could be a psi clause here? Okay, I made a mistake, sorry. the clause number 5 must be negated, a negation CF of C, and this makes sense because now I can resolve this clause with clause number 2, and the resolvent then will be df of C. Exactly. So let's continue. Let's choose clause number 3 as a side clause. And by the way, I forgot to mention that in SLD resolution, the side clauses must be chosen from the input clause sets. Okay, so far we had no other option, but this is an important detail. All the side clauses must come from the input clause set. Okay, so I chose clause number 3, and therefore we must apply the unifier which substitutes C into X, and then the resolvent is not PR of C or CF of C. Then, of course, the best choice is to apply, to choose clause number 1 as a side clause. And then it is very easy to generate the resolvent. And here we are. So here we would like to choose clause number 5 as a side clause, but we cannot because clause number 5 is not an input clause. We definitely must choose a side clause from the input clause set. So we have no other choice than choose clause number 4, and therefore we need a unifier, the same as before, and the resolvent is PR of C. And then, then we can choose clause number 1 as a side clause, and this is how we can generate the empty clause, which proves that the original conclusion formula is a logical consequence of the two premises.